Dear students, welcome back to my course Periodic Table and Periodic Properties of the Elements. Hope you have enjoyed and learned a lot about the how periodic table development took place earlier, and the various periodic properties what we'll be studying under this module. So welcome back again for the module 2. Program goals and program objectives I already explained you. Then under module 2 you will be studying about the effective nuclear charge, then the penetration of orbitals, variation of sp, d and f orbital energies of atom in the periodic table, electronic configuration, atomic and ionic sizes. So all this is the part of your module 2. Under module 1 I already explained you about the effective nuclear charge and the calculation of the effective nuclear charge with the help of the Slater rule. There we were doing the calculation based on the position of the electron of the interest and in which orbital it is. If it is in the s or p orbital, then we are having the different set of calculations, and if the electron is there in the d or f orbital, then we are having a different set of the calculation. So the next topic in the second module is the general trend of energies of various orbitals. So here you can look at it. This is the way how the energy is increasing. This is the 1s. After 1s there is 2s, then 2p, and under p orbital we are having 3 suborbitals px, py and pz. Then here 3s, 3p, then 4s, then 4p, then here we are having the 3d, then 4p, 5s, then the 4d and so on. So all this is the way how the electron goes on in these orbitals, right? Now whenever you want to write down the electronic configuration of the elements, or you can say if you want to fill the orbitals with the electrons, how you will go? So we are having three principles here. One is the Aufbau principle, the another one is the Pauli's exclusion principle, then the third is the Hund's rule. All these three rules collectively supports you for the making the electronic configuration of the any element. So what is the first Aufbau principle says? As per the Aufbau principle, energy levels and sub levels fill from lowest energy to the high. Means it says whenever you are starting your energy electron filling, first the electron will go in the least energy orbital, right? And then what is the Pauli exclusion principle? It says orbitals that are in the same sub level have the same energy. Means if I am saying about the 2p, then 2px, 2py and 2pz, all three will be having the same energy. And it also says that no more than 2 electrons per orbital. Means in a sub level of orbital maximum 2 electron can exist. Now the third one is the Hund's rule. What it says? It says that when filling orbital that have the same energy, place one electron in each before completing pairs. Means if suppose you are having 4 electrons in 2p orbital, then first will go in 2px, second in 2py, third in 2pz, then the fourth one will come now to pair with the 2px. Now the 2px will be having the one complete pair, then the one py and pz, right? So all these three principles are very important while doing the electronic configuration, right? This is the how the various levels are filling. If you want to remember how you will learn this, so you need to write down sorry, 1s, 2s, 1 series, second series, third, fourth, fifth, sixth, seventh and so on. These are the various series. 1s is just having the s orbital, second level is having 2s and 2p orbital, whereas third level is having the, or third shell is having 3s, 3p and 3d, and after that we are having all the orbitals, that is the sp, d, f. Now how this electron filling will start? It start by drawing, you started by drawing a diagram, putting each energy shell on a row like this, right? Then you just transverse or make diagonal and join these diagonal backward. Means next draw arrows through the diagonal looping back to the next diagonal. Means from you need to go to the back. Okay, after 2s it will go to the 2p, then after 3s it will go to the back, means to the 3p. right? This is the way how electron goes on. So if I will start the counting, it is 1s2, 2s2, then 2p6, 3s2, 3p6, 4s2, then 3d10, 4p6, 5s2, and so on, right? Now electron configuration of the atoms in their ground state. Ground state means their the atomic number of the element, right? So if you can write it, suppose you want to write down the electronic configuration for the 36 atomic number, that is for krypton. So it will go like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6, right? This is a long way to write down its electronic configuration. Now if suppose 36 is a very short number, you can write down easily about its electronic configuration. But when you want to write down the electronic configuration, suppose for 70 or 80, then it's a tedious task. So that's another, we are having a shorthand task or way of writing an electronic configuration. How? To use the symbol of previous noble gas in the bracket. Suppose for the rubidium, its atomic number is 37, right? Krypton is 36, means for krypton this is your electronic configuration. After 36 just one electron will remain, and this is the 4s2 is the 4s2, 3d10, 4p6. After 4p6 the electron will go in the 5s1, so remaining this one electron will go in the 5s1, right? So if you want to write down the electronic configuration for atomic number 3, it is 1s2, 2s1, right? Then for the 4 beryllium, it is 1s2, 2s2. Now for the boron, it is 1s2, 2s2, then 2p1. For carbon, it is 1s2, 2s2, and 2p2. Now remember what the Pauli's exclusion principle was. The electron will go one by one to the all three sublevels, then they will come for the pairing, means this electron isn't not going to this suborbital, it will go 1 1 and 1, so on, then the fourth one will come here to make a pair, right? Now the valence electron. So what are the valence electron? The electrons in all the sublevel with the highest principal energy shell are called the valence electrons. Electrons in the lower energy shells are called the core electron. One of the most important factor in the way an atom behaves, both chemically and physically, it is the number of the electrons. Means only the valence electron number decides how any element will react chemically or physically, right? Now irregular electronic configuration. We know that the we are having the a particular sequence of the filling of orbitals like 1s2, 2s2, 1s2, 2s2, 2p6, 3s2, 3p6, then we are having after 3p we are having 4s2, then 3d10, right? It should go ideally, and before going to the 3d orbital the electron goes in the 4s orbital, right? So sometimes it is not going to the 4s completely, means the number of electron which can come here in the 4s is the 2 maximum number, but sometimes it is just 4s1 and it is 3d5 or 3d10, right? I will explain you later on. But the difference is energy is not large. Some of the transition metal have irregular electronic configuration in which the ns only partially fills before the n-1. What I just told you, that ns is having either ns0 or ns1 rather than ns2, and the electrons are going to the n-1 d orbital before it, prior to it. So this type of metals electronic configuration must be found experimentally, right? Now for the chromium, it is the argon. Argon is the noble gas, right? It should be 4s2. After argon the 6 electron remains over there, right? So it should be like the 4s2 3d4 experimentally, because first the electron will go in the 4s2, after that it will go to the 3d4. But experimentally what we are finding? We are finding 4s1 3d5, right? For the copper, ideally it should be 4s2 3d9, but experimentally we are finding 4s1 3d10, right? Then for molybdenum, it is after having the krypton electronic configuration 5s2 4d10 4d4, sorry, and again experimentally we are finding 5s1 4d5, right? So what is the major difference? You can easily check out here the d5, d10, d5, then it should be the F, right? So it is the d4. The maximum number of electrons which can come over here in the d orbital is the 10, right? This is the fulfilled d orbital, this is the half filled d orbital. Means here in both cases we are near to fulfilled or the half filled d orbital. So experimentally we have found that the stability of half filled or fulfilled d orbital is much more rather than the partially filled, right? So these electronic configuration in which you are having the fulfilled and half filled d orbital are much more stable. So these are known as irregular electronic configuration, right? But they are, although they are irregular, but they are actually more stable electronic configuration, right? Now, electronic configuration of cations in their ground state. Cations, when we are having the cations we are having when we are, any element is just leaving an electron, right, or it is losing an electron, then it is the formation of the cation, right? Here in example you can understand, it is the magnesium atom. It is having 3s2 as a valence electron. After losing this electron, it is forming the magnesium plus 2 cation. As it releases the 2 electron, so it is the plus 2 charge over there, right? Now electronic configuration of anions in their ground state, as the by losing an electron you are having the formation of the cation, but if the atom is accepting an electron, then it is having the formation of the anion, right? As for an example, you can see sulfur atom, it is having the 3p4, right? To complete its octet it need 2 extra electron in the p orbital, then 3s2, 2 plus 6 will be 8, that is the complete octet, right? So S anion, sulfur anion, as it gains 2 electrons, so it is the generation of 2 negative, and it is 1s2, 2s2, 2p6, 3s2, 3p6, now complete octet, right? Now properties and electronic configuration. Now as in module 1 I explained you all about the various periods and the families, and I also explained that the elements in the same family as we human have the family have the similar similarities among each other. In the same way here also we have the similarities, right? As if we are talking about this, they are quite similar to each other. Alkaline earth metals, halogens, then noble gases, they are quite similar to each other, right? Now this is the noble gas configuration. Here these are having complete octet, right? Complete octet means they need no more electrons to get the complete octet, so they are very inactive, or you can say they are rarely react with anyone, right? And the complete octet is except for helium, which has only 2 electrons, right? Now the size of atoms and ions. What is the size, or what you can say the radius of any atom or any molecule? The atomic radius of an atom is defined as the half the distance between the nuclei in a homonuclear bond, right? Homonuclear means both the nucleus are same. It is half the distance. This is the total distance between the two nuclei, nucleus distance. If you are doing half of it, then it is the atomic radii, right? So what about its trend? Whenever we are moving left to right, means from here to here in the periodic table, or from up to down in periodic table, how the trend goes on, right? You can see from here, whenever we are moving left to right, the size is shrinking, means it is decreasing. When we are moving up to down, the size is increasing, right? But here in case of lanthanides, you can easily say that the change is not much more. It is not increasing, not decreasing. In between, it looks like that it is increasing, but generally it is not that much, right? I will explain you how this goes on and why. Here, whenever you are moving up to down on a periodic table as lithium, sodium, potassium, rubidium and cesium, you can easily check out here. It is 2s1, 3s1, 4s1, 5s1 and 6s1, means the electron, the valence electron is there in the next shell. After 2 you are having 3, then after 3 you are having 4, then you are having 5, then you are having 6. Means the distance from the nucleus is increasing. That is means it is increasing the distance when you are moving from up to down in a periodic table, right? And whenever you are moving left to right in a periodic table, the 2s1, then 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, means the electron, the extra electron is coming inside the same shell. It is the second shell only. As the number of electron is increasing, number of proton is also increasing, which is increasing the force of attraction between the nucleus and the electron. So due to the increased force of attraction between the nucleus and the electron, the size of the atom is shrinking. That's why. So this is the reason when we are moving left to right in a periodic table, atomic radius decreases, and when we are moving up to down in a group, it increases, right? So this is the trend of the atom and ions sizes, right? Now trends, you can easily, what I explained you, it is having this much size, it is the smaller, and here the trend is going like this, right? Now ion, when the ions are forming, whenever any ion is losing, any element is losing an electron, then it is forming a cation. Here 11 proton, 11 electron. After losing one electron, it is having the excess of positive charge, right? So sodium cation. And whenever any neutral atom gains one or more electron, it becomes anion. Here 17 proton, 17 electron, 17 proton, 18 electron, one more electron added, and electron carries a negative charge, so the chlorine ion, anion. Now cation is always smaller than its atom from which it has formed, and anion is always larger than the atom which has formed, because after losing the electron, right, it is losing its electron from its valence shell. So valence shell is no more exist in the lithium lithium atom, or you can say the size decreases, and fluorine, it is just taking the extra electron, right, and it is getting bigger in the size. Now how the trends, as I explained you in my earlier slide, that the in the transition element, the size of this atoms is not changing much more, because here the extra electron is coming in the n-1d shell. Rather than going to the extra shell, it is going to n-1. You can see here it is 3d2, 3d3, 3d5, 3d5, 3d6, means the extra electron is just coming, which is the place which is already there. So it is not creating extra space to, or it is not diminishing at any space, which is responsible to increase or to decrease the size of the atom and ion or cation, right? So this was all about the atomic or ionic radii, then the other properties. Hope you have enjoyed all these, and you are learning a lot. Keep practicing at your home. Do take care of yourself. Thank you very much.